Um, so we'll conclude our discussion of proximal gradient descent in the short time we have and get on with projected gradient descent. So recap our discussion on proximal gradient descent where we are trying to match the updates, the next updates with respect to the gradient descent step um, for the function f, and we had a function c which potentially may not be differentiable. We would expect it to have a simple form, and all we did was slap on the c to the main function, but through its quadratic approximation around the gradient descent step. So we found a very compact way of writing this: argmin over x of 1 by 2 gamma x minus the gradient descent step plus our non-differentiable function c, right? So this is just a recap again. Now it turns out that if f is convex, sorry, this c, this is not h, this is c. If f and c are convex, then the proximal minimization and the proximal minimization, if it can be solved exactly, ideally closed form, or it can be solved even iteratively but very quickly enough, then discounting the time required to actually solve this problem, right? If assuming that this problem can be solved quickly enough, discounting that time, the the error basically can be bounded by 1 upon 2t. So this is basically the convergence rate for smooth functions, which is good news. So I had left some homework, thought or food for thought rather. We had taken some examples, right? Um, the class I took a specific example, which was Cx as the one norm, of x, right? And there we were able to find a solution. What was the solution? If Cx is one norm, or let's say a lambda times one norm, whatever. Lambda is not required here. Yeah. What did it turn out to be? Which of these forms? Well, it's none of these. All these forms are what? These are all differentiable, right? Except for the Cx is mu x if x is greater than equal to 0 or infinity otherwise. Right? This is a non-differentiable, a not differentiable everywhere. Whereas the ones on the board are differentiable. So we're just doing a sanity check. If it's differentiable, what happens, right? A transpose x or the 2 norm square of x and so on. Okay. So another reason we are interested in the simple forms is from the point of view of calculus of prox operators. So when you want to compose, Cx itself is a composition, let's say of one norm. Let's say I have, and this is often the case, where I have, I don't know if any of you are reading up papers on block norms, right? So let's say x has these blocks, okay? X1, x2, x3. Each of them is vector. So often what is done is you look at overall one norm, but within each block two norm. So any of you have heard of group sparsity? The term group sparsity. So group sparsity basically says one norm gives you sparsity, right? Two norm doesn't give you sparsity. So I could look at the two norm of each of these blocks, okay? And overall I take a one norm. What this basically will mean is a summation of these, right? X, take these group of blocks and sum their two norms. Now instead of one norm, I could have another norm, a row norm, right? So this is group or block sparsity. This comes up in such settings. Okay, so often you will have compositions of some of these simpler forms which are written on the board, and the one we dealt with in the last class. So these C should be easy to handle. Right? What you do is, if in these cases, for example, C is differentiable pretty much everywhere in the domain. So you can just write the optimality condition x minus z plus gamma c prime x is 0, right? Remember what is z? Z is going to be always our gradient descent update. Okay, z is xt minus gamma times gradient of f at xt, the gradient descent update. That's what z is representing everywhere. So I'm going to take a z and find the proximal point, right, around z. So then I ask this question at the end: what if the function is non-differentiable? These should be all easy. You can just solve this function, solve this equation. Okay, there are also some of these texts, instead of defining prox, they have something called prox nu c. So there's a slight difference. We have used gamma and they use prox nu gamma c. In their case, you'll have to treat it as prox nu gamma c. Okay. But we'll stick to our prox gamma. We'll put the gamma in the subscript as on the previous slide. Okay. And this is what we use, prox gamma. Some people put the C there, which means you'll include the you need to include the gamma explicitly in the objective. Okay. So the main ideas of computing prox are as follows. Okay, again, write down the prox operator. Prox gamma z is argument over x oh, sorry, this was okay. So I'm stuck for some reason. Okay, so my homework from previous class was to try out solving. Oh, there's a small typo here. Cx this Cx is 0 if x is not equal to 0 and minus lambda if x is equal to 0. Right? So basically Cx just peaks at at 0 as minus lambda. A Cx peaks at 0 as lambda. Anyone, if you tried this for the prox problem? Right? Anyone? What are the solutions? Okay, so as I said, this z is the previous x t minus gradient update on f. So these are very simple, don't even require, these are simpler than lasso. We have already solved this for lasso, right? What was the case for lasso? Soft thresholding, right? That turned out to be, we defined as soft. Okay, no, gamma there. X was soft thresholding on the lambda on the Z. So these should be much easier. I mean, lambda x cube if x greater than equal to 0 and minus infinity otherwise. Is it sparsity inducing? X greater than equal to 0 gives you lambda x cube. Not at all, right? It's not even having the traits of the one norm of x. So these should be very simple. In fact, here's the answer. Okay, so um, Cx is x lambda x cube. You just need to solve this objective function. X minus z norm square plus lambda Cx. Okay, this is the form I have taken. But if you want, you can put a 1 upon 2 gamma. I do this 1 upon 2 gamma is basically assuming that there's a step size of gamma. And this, you know, the roots of kind of quadratic, you're very familiar with. The quadratic you'll get by setting the derivative to 0. So it will basically be lambda times, so 3 lambda times x square plus 2x minus z, right? So if you solve that, you get 1 plus 12 z lambda minus 2 divided by 6 lambda. So the other two should also be very simple. Okay, so yeah, this is kind of now bringing the perspective which we talked about in the last class, which is if C is non-differentiable, and the classic example is simplified lasso, where Cx is lambda times 1 norm of x. And here, let's say very specifically, Cx is just lambda times the absolute value of x, assuming x is a real number, right? And in which case, this is what you get. Xi is Zi minus lambda. Lambda is, so Zi is greater than lambda. 0 if Zi is between minus lambda and lambda. And Zi plus lambda if Zi is less than minus lambda. Just pushing up a fairly negative lambda, fairly negative Zi by lambda, pushing up a fairly, or pushing down a fairly positive Zi by lambda, and anything between minus lambda and lambda, set it to 0. Okay. So this is just generalizing the whole thing for L1 norm, right? Now you'll have to do this component wise. Okay, this is just recapping the proximal subgradient descent for algorithm for lasso, right? So overall, if you have a so far, sorry, all this was fine as long as I was just solving this objective function. But now I want to plug this in a larger scheme. What is the larger scheme? Fx is phi x minus y norm square. That's my objective, plus a Cx, which is the one norm of x. Now I need to solve this. This has to be done iteratively. This cannot be with one step of soft thresholding. So we'll have to do this iteratively. Take xt plus 1. Sorry, compute the zt plus 1, which is the gradient descent update from the previous iteration. And then do a prox using a soft thresholding objective. And then update your xt plus 1 for the next iteration of soft thresholding. Right? So this is how it will proceed. So zt plus 1 is the next gradient descent iterate, compute the prox operation, compute the prox zt plus 1 using the soft thresholding. These 3 steps which we discussed several times already, and then move to the next iteration. Okay, so some of this now we have discussed in the class. Okay, so simplified lasso, you have an idea how to do it. We also, I have kind of alluded how this can be solved. A simple problem such as lambda x cube, x greater than or equal to 0, and infinity otherwise. You can similarly try and solve for these. Okay, but what I'll do is, instead of trying and solving, just give you the intuition. This should not be very difficult, right? Minus lambda log x. What would you do? Minus lambda log x. You take the derivative. It's differentiable, right? Of course, the inequality is going to be important here. So let's consider the case x greater than 0. Minus lambda log x will give you 1 upon I mean minus lambda by x, right? When you take a derivative of cx, this will be x minus z, again a quadratic, right? Just like x cube give you a quadratic, log x will also give you a quadratic to solve. So that again can be, these are the roots of a, these are obtained as roots of a quadratic. Um, the last one, see the last one is interesting because you are having lambda x as a penalty, right? The lambda x cx as penalty when x is between 0 and alpha. Now if you look at the solution, what is it doing? It's saying that the solution cannot exceed alpha, right? If you look at this entire thing, min of max of z minus lambda comma 0 comma alpha, so it cannot exceed alpha, which is what we wanted, right? It's infinity otherwise, so you should not let it go to infinity, and that's the max value. What's the min value? 0. So it's kind of wondering what you want. And what is it doing otherwise? It's otherwise shrinking by lambda, right? Which is also intuitive, lambda x. So shrink it by lambda. Okay, so um, so just to kind of summarize, simplified lasso is just taking a max of 0 comma a, right? Um, this lambda x greater than or equal to 0 and infinity otherwise, it's again ensuring that the um, the value remains greater than or equal to 0. Otherwise, shrink it by lambda. As long as it's greater than or equal to 0, shrink it by lambda. The third and fourth one I won't get into again. But by design, they are going to be greater than or equal to 0. We're only considering the roots that are positive. The final one, this is a regularizer operating in some interval, and it's going to be less than or equal to alpha and greater than or equal to 0, and shrink the z by lambda otherwise. I'm sure now you're in a position to be able to solve these. You can do this for more complex settings as well. So constant is of course trivially the identity prox operator. But if it's affine, you'll just need to shrink by the transformation A, okay, z minus A. If it's convex quadratic, C, as I said, these differentiable cases can become interesting when you're looking at compositions. And the next table will be compositions, right? So all you need to do is move that A by an identity and take an inverse of this. Basically, this is a rotation. The z minus b is exactly like in the affine case. You're just shifting the z by b. Okay, so so now what happens? Okay, so there's an interpretation here as well. The a plus I whole inverse is a kind of preconditioning. Okay, so there's a quadratic component here, which is sitting as penalty here. C. This is quadratic component, and the resultant prox update. It's saying, well, I'll take z minus b, but I would like it to have a certain transformation in the space, and that transformation is often known as preconditioning. Okay, so it's creating this orientation. Now this orientation also has an I. So basically, you're trying to ensure that the resultant output is better conditioned. Generally, when you have an identity sitting there, right? Identity matrix has all eigenvalues as 1, right? I mean eigenvalues as 1. So it's supposed to be well behaved. It doesn't have a very skewed max to min eigenvalue ratio. So any such kind of multiplication you consider to be preconditioning, so that you improve the conditioning of the matrix, you improve the skew between the max and min eigenvalues. Okay, so now calculus. Calculus is where you have cases like this addressed. What if you have a block sparsity inducing norm? Okay, so as an exercise, you should figure out which of these cases does our block sparsity fall in. Okay, so the first is sum of components. So sum of components, the prox will become product of the respective components. Does R fall in that category? Sum of the CIs. Yes. Can I realize the one norm of two norm blocks of two norms using this property? Yes, right. So the first one itself fits. Yeah, so this is good enough for us. And basically, what we'll have is a prox over each of these x1, x2, x3, and so on by wiping out the other components. That's the answer. Second is C of lambda x plus a. So as expected, this should just be a simple linear transformation. This is just linear here, lambda z plus a minus a. But the prox is on lambda z plus a. Adding the you're computing the prox after adding a and then subtracting that a again. Okay, so on the third one, you have a C of 1 upon lambda x. Okay, so what this results in, maybe it's not visible here. So what this results in is division by lambda in the prox function, the prox component, prox of C divided by lambda. Um, this one is again interesting. So taking from our quadratic expression, Cx plus, if you have a Cx, existing Cx, add a transpose x plus beta by 2 x norm x square, it again results in this preconditioning. Sorry, if it's not visible, let me go to the previous slide. There's 1 upon beta plus 1c. So this beta from the x square is being applied here. There's a kind of preconditioning. Okay, and then the last two, this is again very close to what we saw in the previous slide. So I'll not go into these. Okay, so this basically sums up how you can compose non-differentiable functions with differentiable functions and yet get simple prox updates. These are very, as you can see, most of them are very simple updates on the prox side. So proximal gradient descent is basically gradient descent for the special case of H or the C. Actually, I meant C here. Sometimes I use H. So this, if the second component is set to 0, if f is 0, so that's also possible, right? Your main function f could be 0, which means what? What does it mean? This part is vacuous. The first part is vacuous. So then it turns out that you're basically minimizing C alone. So people have also studied that under proximal point algorithm. Key to proximal gradient descent is the step I've written on the board. It should be solvable in very reasonable amount of time. There are also other papers, inexact proximal gradient methods, where prox can be computed approximately. Okay, so how does that reflect in the convergence time of the main algorithm? It's still not very well studied. There's I think couple of papers only. However, what is interesting is you can apply the accelerated method to proximal gradient descent. So yeah, so these are the 2 points. So there's this notion of generalized gradient descent, which we saw. What I'm going to leave as a homework problem for you is a special case. So far we have discussed the solution to this when C is differentiable, or composition of differentiable and non-differentiable functions. What if C is the identity? C is the indicator function. What if I get C from constraints? Okay, so I think this is just a slide on how accelerated gradient descent can be applied, and you can see even with accelerated gradient descent, you can actually get a lot of gain. I'm just going to leave you with this one slide for thinking. So what happens if you have C to be a sum of indicator functions coming from constraints? So we saw some constraints today, right? Now these constraints, let's assume for the time being that they are convex constraints. Would it result? Would this inclusion of convex constraints result in a proximal step which is solvable exactly? um, are there necessary and sufficient conditions for the prox step having optimal solutions when you have constraints in place of C? Okay, so just think about it. In fact, here's just a nice table for you to mull over, right? And it's a very nice book, by the way. Um, it's a nice book. Um, I forget the name of the author. Nathan Beck is the name of the author. So these tables you'll find in that book. So it's just as I showed the table for the procs, right? Here again you can see simple constraints, right? For example, if you have a constraint that the z variable or x variable should be the positive real line or positive half space, then the solution turns out to be the proximal solution turns out to be just project whatever if my x turns out to be. So I'll just conclude in 2 minutes. So if C is simply that x should be in Rn plus, right? That's what you see there. Then the prox solution is nothing but z plus, which means if z is less than equal to 0 or zi, then the prox component will be 0, right? And z otherwise. So if it's greater than equal to 0, keep it to be z. If it's less than equal to 0, then push it to 0. So you see, very simple update, intuitive, right? This is simple projection. But it turns out that this is a solution to the proc step under the under these constraints. So a couple of others, box LU, right? If you have an upper bound and lower bound, all you're saying in this projection is clip it. If it's above the upper bound, clip it to upper bound. If it's lower than lower bound, push it to the lower bound. So how are these solutions arrived? So that's what we will discuss next time, starting next class. The necessary and sufficient conditions for constraint optimization, the KKT conditions, which was brought up, right? Karush-Kuntakar conditions. But all those are basically very useful to determine proximal solutions under projection. Thank you. So we won't meet on Friday. We'll meet on next Monday. So I went a little over time because we will have to miss the Friday class. Thanks.